Okay, so this lecture we're going to talk about the thermodynamics of amphiphilic self-assembly. So this process is interesting to anyone who cares about biomaterials. We know that macromolecular and biological systems can self-assemble into really important, interesting and important structures, into things like membranes, right, which are obviously important for cell structures, vesicles, which are a little bit less complex than membranes, and other complex morphologies. So that can include worm-like structures, so you can have membranes, which typically have maybe a double layer associated with them. You can have vesicles that are just some kind of surface. You can have worm-like structures like tubes that form. All kinds of different morphologies can be created spontaneously by biological molecules or by amphiphiles. And so we want to discuss these kinds of soft materials. So what distinguishes these soft materials from things like metals or oxide glasses? So soft materials are dominated in their structure by the kinds of bonding that are applicable. So in particular, there are van der Waals interactions, hydrophobic interactions, hydrogen bonding, as opposed to metals and other hard materials that are dominated by things like covalent, ionic, or metallic bonding, right? And so as a result, the phases formed, so as a consequence, phases formed are dependent on temperature and concentration, and also pH, right? And of course, the phases in hard materials are also dependent on the temperature, but since the energies associated with these kinds of bonding are so much smaller than the energies associated with these kinds of bonding, we tend to see very dramatic changes at lower temperatures. So whereas phase changes that happen in covalent ionic and metallic bonding, like between melting or melting temperatures, tend to be fairly high, temperatures for the dissolution of the structures associated with biomolecules tend to be around room temperature. Okay, so when we think about these amphiphilic molecules, they typically have polar and nonpolar groups. And so typically when we draw them, so if we think about an amphiphile, they typically have a head group and a tail group. And since the head groups tend to be hydrophilic and the tail groups tend to be hydrophobic, you tend to get aggregation of the head groups and the tail groups, right? And so typically these amphiphiles then can form, can aggregate in different ways. So we can get from these amphiphils formation of we can just have simple monomers. We can have dimer groups forming, so we can form trimers, so groups of 3, or any general kind of arrangement, right? So you could form some very complicated structure, so general N-mers, okay? And all of these are possible, and so what we want to know is under what circumstances will we have different size aggregates in our system? Right? So when will different sized aggregates form? Okay, well, what can equilibrium thermodynamics tell us, right? So equilibrium thermo, right, tells us that the chemical potential of identical molecules in different aggregates must be equal. So if we look at the same amphiphile and we look at the amphiphile in a monomer that's just floating freely in the solution, and we look at an amphiphile that's sitting in the dimer, and an amphiphile that's sitting in a trimer, and an amphiphile that's sitting in some N-mer, those all have to be the same. Those all have to be equivalent, otherwise it wouldn't be an equilibrium. Right? Otherwise, the amphiphiles would start moving from, let's say, 3 aggregates with 3 molecules to aggregates with N molecules. So we want to start by writing down an equation for the chemical potential associated with an aggregate of size n, and we can do that by writing mu sub n, right? We're going to write it as mu sub n0 plus kt over n natural log an over n. So where an, remember, is the activity of the molecules in a aggregate of size n. Okay. And where mu n0 is the chemical potential in an aggregate of size n. Arising, but this is not the full chemical potential, this is just the part arising from interaction-free energy. So basically, the way we should look at this is that this is the term that's coming from the various kinds of bonding, the van der Waals hydrophobic hydrogen bonds between the molecules. How much energy does the molecule have when it's sitting in that aggregate? And this part's coming from the entropy. This part's coming from how the molecules are partitioned between the different size molecules, the different size aggregates. And notice that we have a kt over n. This should look familiar from the problem we looked at in the Flory-Huggins model, right, where we said that the entropy associated with an aggregate has to go down as 1 over n as the aggregate grows because we're taking away degrees of freedom, right? Then suddenly those 2 molecules or 3 molecules or n molecules are sort of stuck to each other, and they can't explore the phase space independently as they would if they were monomers. And then similarly, we're saying that the activity of a given molecule varies with n, that It's related to how many molecules are in the aggregate. Okay.